The method of Lagrange multipliers is useful in contexts where you are asked to optimize a function, whether it's finding the max, the min, or both in some cases, and you have a set of constraints, right? So you don't just have the freedom to choose to find any max or min that will satisfy that function. You need to figure out what's going to work within a set of constraints. That's why the method of Lagrange multipliers is useful. So in section 7.3 that we just finished, we found optimal solutions to a function with two or more variables without any constraints. There were no boundaries given to us. We could have had any answer we wanted to, as long as it gave us the optimal solution to your function. In practice, though, applications are going to have constraints or closed boundaries. You're not going to have unlimited resources. You're going to have fixed resources that you have to stay within, and that is going to be your constraint. To optimize functions in terms of one variable, so this would have been something we learned about earlier this semester, that we restricted the domain. Domain, we said x can only be maybe bigger than 0 or between 0 and 10 or something like that. And then we used the extreme value theorem if it was bounded to determine the max and min values of the function, right? So when in the case of two variables now, instead of just one, we are going to use the same kind of process, except we're going to have this constraint equation, right? So you're going to have a function that you want to optimize, and it's going to say, figure out the max or the min of this function as long as this particular relationship between x and y is satisfied. And that relationship is what we call g. G of xy is your constraint. So g of xy is going to equal some constant, some k value, which is a constant, right? So the critical points that we end up finding, x, y, or if you want to consider them a, b, it doesn't really matter, that you're going to find have to also make the constraint equation true. That constraint equation must be made true. And so that's what you want to focus on as well. So we're going to introduce something called the Lagrange multiplier, which is the Greek letter lambda. Lambda is our Lagrange multiplier. It can also be considered a proportionality constant. I'm not going to get into a lot of the details. If this were a theoretical calc class, we would get much deeper into what this Lagrange multiplier is doing. But for now, consider it just to be another constant, okay? Lambda is going to be your constant. Sometimes it's a variable, sometimes it's a constant. Depends on how you're differentiating. The method of Lagrange multipliers, like I said, was developed to solve applications where a function is maximized or minimized subject to a constraint, right? We only have fixed resources, maybe labor hours, maybe money that we can spend, maybe materials that we have available. So that's our constraint function. So the first step you want to do is determine that function you want to optimize. That's going to be typically given to you. We're going to call it f of x, y in general, but it could be cost, profit, revenue, whatever. Number two is going to say determine the constraint equation. We're going to call that g of x, y, right? Set it equal to 0, so that just means subtract that constant k over to the other side. Now it's equal to 0. It's easier to differentiate then. Third step, find what we call the Lagrange function. This bad boy is the Lagrange function. Now, yeah, you should memorize it, but I'm going to show you an alternative to solving instead of needing to understand the Lagrange function. But let's go from there anyway. The Lagrange function is what you're going to construct. That's capital F. The next thing you want to do is step number 4, which is where you want to calculate all of these three partial derivatives, make your system of equations, and set each one equal to 0 and solve. You have three things to solve for. You would need to find x, y, and lambda. Okay, those are the three things that we're solving for. Hence, we need three equations. Now, I'm going to give you this alternative because I like how the book discusses how to work out this solution. As an alternative to steps 3 and 4 up here, 3 and 4, you could just set up this system of equations. Okay, notice there's still three equations, and solve simultaneously. You're still finding the same thing, x, y, and lambda, but it's treated just slightly differently. The students seem to understand how to use better. So that's this note. That's how I'm going to be solving my equations. And honestly, it doesn't matter which one you choose. All right, so here's an example. We have a function f. We have to find the optimal solutions subject to a constraint, right? So this constraint, 8x squared plus y squared equals 1, maybe rewrite that 8x squared plus y squared minus 1 equals 0, right? So what we're going to do is we're going to find 4 partial derivatives. The partial derivative of f with respect to x is first. So go up to f, x is your variable, y is going to be a constant, and we're going to find the derivative. Next, we find the partial derivative of f with respect to y. So this time x is your constant. All right, now we don't just set these equal to 0, solve for x like we did in the previous section, because once again we've got this constraint that we want to make sure is also satisfied. We want that constraint function to be satisfied. So we're going to find the partial derivative of that function, which we call g, with respect to x, and also with respect to y. Okay, so now we set up your equations involving the Lagrange multiplier. That's the lambda, right? The equations that we're going to come up with are here, right there. The first one is going to take your partial with respect to, partial of f with respect to x. Let's do some highlighting here. That part right there, equal to lambda times that partial, okay? The next one is going to use the partials with respect to y. So once again, that first equation is going to say 16x minus 24y equals lambda times 16x. And the next equation will say negative 24x plus 2y equals lambda times 2y. So pause and take a couple minutes if you need to understand where that's coming from. Now, the system is not quite complete. We also need to throw in there that constraint function. So this is now your system of equations that you want to solve for x, y, and lambda. All right, so one approach is to take those top two and solve each of them for lambda, and then set them equal to each other. So if I take the top equation and get lambda by itself, that's going to mean divide both sides by 16x. I'm going to do them separately so you can see how they simplify. And that's going to give you 1 minus 3y over 2x. The second equation, I'm going to divide everything by 2y. And that's what you got. So now, like I said, I forgot the equals lambda here. You're going to set the results equal to one another. Okay, set those equal to each other. It's going to say those ones are going to cancel out, aren't they? The plus ones cancel out when you set them equal to one another. You end up with negative 3y over 2x equals negative 12x over y. Let's see, what should we do? We should cross multiply here. We're going to get negative 3y squared equals negative 24x. I can divide out a negative 3 since that's evenly done on both sides, leaving you with y squared equals 8x. Y squared equals 8x. Now that's great. So all I did was I took the top two equations, I solved them each for lambda. Okay, and then I took those results and set those equal to one another and just played with it a little bit until I saw something that was going to be useful. Now, how do you know how to play with it and how to know if it's useful? Well, don't forget that third equation that you're subject to up here. As soon as you see something something come about from your work over here on the left that can be used in that third constraint, that constraint equation, such as a y squared. Look up here, there's a y squared. They appear in both places. I can do a substitution right now. I can take this 8x and put it in right there for y squared. And now what you have is 8x squared plus 8x minus 1 equals 0. Wondering if something got lost. It surely did. It surely did. I forgot my x squared. Yeah, right here. When I multiplied that 2x times the negative 12x, I forgot my x squared. There. Okay, so the y squared that's up in the constraint equation with my arrow next to it right there, that's going to get replaced with 8x squared. Now you're going to get what, like terms? We have 16x squared equals 1 if I get the 1 on the other side. X squared equals 1 over 16. X equals plus or minus 1/4. All right, so what we have to do at this point is figure out all of the corresponding values of y that go along with each value for x. In other words, if x equals 1/4, how much does y need to equal? And to figure this out, you're going to utilize that that constraint equation, right? So if x equals 1/4, you're going to put the 1/4 in right here. And you're going to solve for y. And when you solve for y, you should get, let's see, 1/4 for x. Y is going to equal, let's see, y squared is going to equal 1/2. Let's give you that step. And so that means that y is equal to plus or minus the square root of 1/2. That's going to give you two ordered pairs right off the bat. It's going to give you positive 1/4 for x, I'm running out of space, and then a positive root 1/2. Okay, you could simplify that a little bit. That's going to give you a 1/4 for x and then a negative square root of 1/2. You can do the same thing when you plug in negative 1/4 x. For x, you're going to get the same exact results. And that's going to give you all four solutions that are going to either max or min the given function f, subject to the constraint. You have four different places. Now to figure out which ones are maximums and which ones are minimums, you're going to have to plug in the values of x and y back into this beginning equation back there and figure out what f of those values give you. F of those values, just it's a matter of using your calculator. You're going to end up getting negative 3.24 on that first one, 5.24 on the one below it, $5.24 on that one, and then negative 3.24 once again on the bottom one. And so the two that gave you negative 3.24, those are going to be considered minimums. Minimum and minimum. Should have left you more space. And then the others that gave you positive 5.24, those are your maximums. Okay, so that tells you where to find the minimum, where to find the maximum.